Hello, my name is Aiden Nguyen, and this is Lab 1 for constant velocity. So the purpose of the experiment is to demonstrate the motion of an object under constant velocity, both in the real world and in simulation. So this experiment also examines the variety of Newton's second law and how the lack of a net force manifests in an object's velocity and its change in position over time. So to test the accuracy of this law, graphs of horizontal position versus time for both observational and simulated models are compared. So the momentum principle describes how the net force acts on a system, creating a change in momentum over time, which gives us these formulas. So with this principle, two formulas necessary for this lab are derived, one to update the object's velocity after a certain period of time, and one to update its position. So before tracking the motion of the chosen object using the tracker software, we calibrated the tracker software in terms of scale to the object's diameter. Then each frame is marked, and the change in position from frame to frame is plotted by the software. The data obtained by this model creates the initial conditions for the simulated constant velocity model later. So here we just have a video of the tracker software. You can see how the tracker software tracks the center of the ball and its position every frame, and you can see how it creates this positive linear relationship with the constant slope. So using the data from the tracker program, we can create initial conditions for the computational model. The system is, of course, the stress ball, and the surroundings is everything else, including the table and the earth. And we can say that the F net is 0 because we can assume that air resistance and friction are negligible or non-existent, because to maintain constant velocity observed in the experiment, there has to be no net force acting on the system, as stated by Newton's first law. So therefore, the model for constant velocity has to lack net force. So here are the other initial conditions, such as the initial position and the initial time. So using these initial conditions plus the position time of the next frame, the initial velocity can be calculated, because theoretically, the initial velocity should be equal to the average velocity. Therefore, we can use the relationship such as this, the change in x over the change in time, to calculate out the initial velocity. So using the formulas derived earlier, we can represent them with variables in code. So the important thing to note about this is that this section highlighted here will equal 0 because F net equals 0. So in other words, the lack of a net force creates a lack of acceleration, so the initial velocity will be equal to the final velocity. So here are the coded variables and what they represent. Most important to note are the time step size, which is set at 1/30 because of the frames per second of the tracker software, and the end time, which is just the final time marking of the tracker software. So here we just have a video of the model, and we can see how it resulted in a positive constant slope. So here we just have a comparison of the two graphs. We can see that the glow script graph definitely had a more constant slope, and it reached a higher position than the tracker software, because we can see that the tracker data points began to slow down over time, and the velocity began to decrease. We can say that this was because there must have been some net force causing the system to decelerate over time. So some sources of error may include deviation due to the net force. In reality, we said that air resistance and friction were negligible, but in reality, they do affect a system and did cause the ball to slow down. And also, the tracker software had shifted initial values. You saw that they did not equal 0. So those may have affected the accuracy of the model. If the axes were flipped, the magnitude of change in position would stay the same. Therefore, the deviation between the experiment and the simulation would still be reflected. However, directions would be reversed, which means that the stress ball would be moving in the negative x direction at constant velocity, which would create a downward sloping linear graph. So it's impossible to know how many forces are acting on an object at once. So, which is because there are many small scale forces acting on an object at any given time, such as gravity between masses or air particle collision, that make it near impossible to actually create a net zero force outside of a perfect vacuum. So in conclusion, we learned that for an object under constant velocity, there has to be no net force, and in a predictive model, this is valid, and the object will move with uniform motion. However, the observational model demonstrates how objects in the real world actually experience forces that sum to create a net force that affects velocity, which makes sense with the definition of Newton's second law. So thank you for watching this.